Hello guys, today we'll be looking at what is referred to as transformation geometry. And yes, for those who have watched the Transformers movie, you know exactly what I'm talking about. What happens in the Transformers, and why is the movie given that title? Now when we look at those cars, we see them change position, we see them change size, we see them change shape. That is exactly what transformation geometry refers to. It refers to change in position, shape, size, orientation. All of that comes together to form what we call transformation geometry. Now, think of you walking from Spalding to Mandeville. You'd have changed your position. Now, notice that you wouldn't have changed your shape, your size, or anything, but your position would have changed. That is one example of a transformation. Think of somebody else who is probably making some dumplings. All right? You start out with a flour, and then you end up with your dumpling. That is an example of a transformation. Think about a plane flying across the sky. Here's the next conceptual idea. You buy a balloon, you take that very small balloon and you blow it up. What happens is that the balloon is enlarged. So we refer to that transformation as enlargement. Think about the planets rotating around the sun. Alright? That is an example because the sun is a central point and the planets go around it. That is an example of a transformation. So all of these come together to form what we call transformation geometry. And we're going to show you how we apply this now in terms of demonstrating movement. And you can even think about yourself looking inside of a mirror. What happens when you look inside of a mirror? If you walk towards the mirror, your image seems to walk towards the mirror as well. So here we have terms coming out like object and image. You will be the object, and whatever you see in the mirror is your image. And the mirror is particularly fascinating because there are some things that happen, like your left side seems to appear to be your right side, and so on. A term refers to as lateral inversion. So all of these terms will come out in transformation geometry. Now, under transformation geometry, the first transformation that we're going to be looking at is what we call a translation. Now, as we spoke before, a translation really means a change in position. And here we're looking at transformation geometry in terms of a two-dimensional plane. So we could probably look at something as a simple board game, probably a game of chess, where you can actually move forward, backward, you can move from left, you can move right. Right? Now, of course, when moving pieces in a chess game, I am sure that if you look at the second property here, is that the size of those objects will not change, they remain the same. Their shape will not change, their shape remains the same. But critical is that their orientation remains the same. And what do I mean by that? Let me just simply put in a simple triangle right here. So this is my triangle. If I were to move that left or move it to the right and then up, the triangle would have the same orientation. So it's actually facing the same direction. If I were to push up the smaller triangle and push it forward, so let's say we move it up and we move it forward, when it gets to this point, it will actually overlap because the orientation is the same. So it doesn't matter where you move that triangle, it will have the same orientation. Here's an example. Now here we have an object. I'm calling it the object because this is what I'm going to carry out the translation on. Alright, now let us identify the coordinates of my object. So we have A, B, C. The coordinate of A is -9, -1. The coordinate of B is -5, -1. And the coordinate of C is -5, -4. And you can see them up here in blue over here on the top left hand corner. That is the coordinate of my object. Now if I'm going to move this object, whether horizontally or vertically, then of course I'm going to need what is called a translating vector. So I need a vector to translate this, to give me first a horizontal movement and then a vertical movement. As you know, when stating a vector, we take the horizontal direction first and then we take the vertical direction. So we have our object, and now I have my translating vector. We're using the vector down here in the bottom left hand corner, which is 2, 4. So my translating vector is 2, 4. So let us translate this object using my translating vector 2, 4 and see what happens. And this is my GeoGebra software. So I'm going to be doing a translation. I'm going to click on my object and I'm going to click on my translating vector, which is 2, 4. See what happens. Now, so we have our object here in red and we have what is called our image here in blue. All right. So when it undergoes a translation, what we initially start out with is the object, but what we get is what we call the image. Now let us compare the points. Bear in mind that my translating vector was 2, 4. Look at point A and look at A prime. Now let us observe first of all the orientation of the object and the image. Look at the object and the image. If you look carefully at them, you notice the orientation is the same. The size is the same. The only thing that would have changed is my position. Now look at point A. Bear in mind that my translating vector was 2, 4. Look at point A, which is -9, -2. Look at A prime, and we use A prime now to label my image. So I know that A is my object, so A is a point on my object, and A prime is a point on my image. So I'm moving from -9, -2 to -7, +2. Look at B. For B, on my object I have -5, -1, but if I look at B prime, the coordinate is -3, 3. And look at C. When I look at C, the coordinate of C is -5, -4, but look at C prime. The coordinate is -3, 0. Now, when I look at my object, I look at my image and I look at my translating vector. Bear in mind that my translating vector was 2, 4. How could I get the image from my object in an algebraic manner? So let's go back to A. I am at -9, -2. Then we're at -7, +2. So notice by adding the translating vector to each point, then I'm going to obtain my image. So I have -9, -2. If I add that to my translating vector, which is 2, 4, I'm going to end up with -7, +2. And of course, the same principle would apply for B and B prime and C prime. And we're going to show you how we actually add this to get the points here. Now, based on what we did with the GeoGebra software, let us manually carry out this transformation. Now, we all agree that my coordinates are A, -9, -2, B, so on. My translating vector, T, I'm going to call it 2, 4. The good thing about all coordinates is that all coordinates can be represented as position vectors. So, to get A prime, which is of course, a coordinate on my image, we all agree that we can say this would be equal to A plus the translating vector. A similar concept will be applied to B prime. So B prime would be equal to B plus my translating vector. And of course, the concept follows through for C prime. So C prime would be equal to C plus my translating vector. And of course, if I'm referring to A as a vector, I could probably say OA, OB, OC. All right? So this is what is going to happen. So A prime will actually become as a vector. And of course, we're talking about OA prime now, coming from the origin, because all coordinates are with respect to the origin. And of course, once you have a coordinate, it can be converted into a position vector. So when I add the corresponding coordinates here, which is -9 plus 2, I'm going to end up with -7. And -2 plus 4, I'm going to end up with +2. B prime, here I'm going to end up with -5 plus 2, so that's -3. -1 plus 4, that is 3. And C prime, bear in mind that these are vectors, so I should really be saying OA prime, OC prime, and OB prime. -2 plus 3, -5 plus 2, that's -3, and -4 plus 4, that is 0. And we do realize that from our software, these are exactly what we ended up with. But bear in mind that these are vectors. So now I need to state the coordinates of the image as coordinates. So therefore, the coordinates of the image And of course, my images here is A prime, B prime, C prime would be A prime as a coordinate, so that's -7, 2. B prime as a coordinate would be -3, 3. And C prime written as a coordinate would be -3, 0.